Welcome to another episode of Learning. I thank each one of you for watching my videos all these years and encouraging me. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We continue the discussion of the solutions of the problems that have appeared in CSIR National Eligibility Test held on February 28, 2025. In this video, we discuss the solution of a problem from the section Algebra, in particular from the group theory, and the question is related to a new concept of the divisible group. Right. This question is placed in part C, which is a multiple select question. There can be more than one answer, and the question carries 4.75 marks. The question ID is 704166. This question is suitable for all these examinations. Right. The given question is a group G is said to be divisible if for every y belongs to G and for every positive integer n there exists an element x belongs to G such that x power n is equal to y. So this is a new concept, and this is the definition of a group G to be called as a divisible group. A group G will be called as a divisible group if for every y belongs to G and for every positive integer n, there exists an element x belongs to G such that x power n is equal to y. Then which of the following groups are divisible? We are given four options. Option 1, Q, a set of rational numbers with ordinary addition. Option 2, C minus the singleton zero, that is the set of non-zero complex numbers with ordinary multiplication. Option 3, the cyclic group of order 5. Option 4, the symmetric group S5. Right. Let's now discuss the solution of the problem in detail. We are given a definition of a divisible group. A group G is said to be divisible if for every y belongs to G and for every positive integer n, there exists an element x belongs to G such that x power n is equal to y. That is, for every y belongs to G and for every positive integer n, the equation x power n is equal to y has a solution for x in G. Let's now take the options one after the other. Option 1, Q with ordinary addition. Q, the set of rational numbers under the usual addition, that is Q plus is a group. We have the group this one. Let y be any element of Q. Let n be any positive integer. Now x power n is equal to y will imply x power n in Q plus means x plus x plus xn times, that is nx is equal to y. This implies x is equal to y by n. Y is a rational number and n is a positive integer, which is again a rational number which is not equal to 0. The quotient is also a rational number. So x power n is equal to y has a solution x is equal to y by n in Q. These steps can be retraced back. That is, x power n is equal to y implies and implied by nx is equal to y implies and implied by x is equal to y by n belongs to Q. So, thus, for every y belongs to Q and for every positive integer n, there exists an element x is equal to y by n belongs to Q such that x power n is equal to y. So, the definition of the divisible group is satisfied. Therefore, the group Q plus Q under usual addition is divisible. Thus, option 1 is true. We mean the group given in option 1 is true. Right. We continue in the next slide. So, that's the definition of divisible group. Option 2, C minus singleton 0, that is, the set of non-zero complex numbers forms a group under ordinary multiplication. Is it a divisible group? That is the question. So, we have the group C minus singleton 0, non-zero complex numbers under multiplication is a group. Let y be any element of C minus singleton 0. Let n be any positive integer. Now, x power n is equal to y will imply x is equal to the nth root of y. Y is a non-zero complex number. The nth root of a complex number exists and is again a non-zero complex number. It belongs to C minus singleton 0. So, the equation x power n is equal to y has a solution in C minus singleton 0. The solution is x is equal to y to the power of 1 by n. The nth roots of a non-zero complex number always exist. They are n in number. So, x power n is equal to y implies and implied by x is equal to y to the power of 1 by n belongs to C minus 0. Thus, the definition of the divisibility is satisfied. Thus, for every y belongs to C minus singleton 0 and for every positive integer n, there exists a x that is equal to y to the power of 1 by n, the nth root of y, which is again a non-zero complex number such that x power n is equal to y. Thus, the group C minus singleton 0, the set of non-zero complex numbers under multiplication is a divisible group. That group is divisible. Thus, option 2 is true. We mean the group given in option 2 is divisible. We move to the options 3 and 4 in the next slide. Right, we are given option 3, the cyclic group of order 5. Right. Let G be a cyclic group of order 5. Assume that G is divisible. Let Y be any element of G, Y not equal to E, that is a non-identity element you take, and M is the order of G is equal to 5. Because G is divisible, there exists a x belongs to G such that x power m is equal to y. That is, x power m is order of G is equal to y. Now, where are we? We are in the group G and x is an element of G. So, x power order of G is identity by a consequence of Lagrange's theorem. Y is equal to x power order of G is identity by a consequence of Lagrange's theorem. This is a contradiction. Why? We are getting y is equal to E, but our choice of y is y not equal to E. So, this contradiction says that our assumption that G is divisible is false. Therefore, G is not divisible. Therefore, the group G is not divisible and option 3 is not true. We mean that the group given in option 3 is not divisible. We make a remark here. The remark is, it may be noted that we have used only finiteness of the group, that is M order of G only, but we have not used the fact that the group is cyclic. That means the cyclic nature is not at all used. So I say this argument can be generalized. And what is the general result you can get? Every finite group G not equal to the identity element alone is not divisible. That's the result. And the proof is just the same what we have given here, but however, I'll show you very quickly. Let G be a finite group. Order of G is equal to M greater than 1. Assume that G is divisible. Let Y be any element of G, Y not equal to E. Since G is divisible, there exists a X belongs to G such that X power M is equal to Y. By Lagrange's theorem, X power M is X power order of G, where G is a finite group, is equal to identity. Thus, Y is equal to X power M is identity, a contradiction to the choice of Y. Our choice of Y is Y not equal to E. This contradiction says that our assumption that G is divisible is not true. Hence the result. Right. That's the general result you can give, and this is the proof. And now we call on option 4 the symmetric group S5. What is S5? Symmetric group S5 is a finite group whose order is 5 factorial, that is 120. And it is a finite group. It is a finite group and is not a trivial group. Therefore, it is not divisible. The symmetric group S5 is not divisible since it is a finite group of order 5 factorial. Use this result. So this is not divisible, and option 4 is not true, meaning that the group given in option 4 is not divisible. Right. Summarizing all the options, the answer to this question is options 1 and 2. That is the detailed discussion of the solution of this problem. In this, we have used only the fact that we have used only Lagrange's theorem in this one. But otherwise, the question is completely based on the given definition. Most probably, this definition of a divisible group, I don't think that will appear in any book like J. A. Gallian or a Topics in Algebra by Herstein or in any other standard textbook what we refer at a MSc level. But however, the student should have an open mind. He has to accept the definition and get the results. So that kind of a skill a student should have. So with these few words, I say, I am sure that you have understood the solution of this problem. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. I am sure that we are going to meet you once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.